All right, guys. So in this chapter, we're going to talk about heat and the first law of thermodynamics. So the unit of the chapter is to define heat and understand the difference between heat and internal energy, and look at heat as sort of like a mechanism for energy transfer. Specific heat is sort of like, let's say, a constant, a proportionality constant that we use as a sort of like an application for heat. Then another application is calorimetry, where we can combine this idea of heat and conservation of energy to solve problems involving energy added to the system to increase temperature or change the phase. Latent heat is a type of energy that goes into changing phase. Um, and after we kind of look at this particular, section of the chapter, which talks about heat, specific heat, latent heat, then we're going to go into first law of thermodynamics. First law of thermodynamics then combines two types of mechanism of energy transfer into the system, where those energy transfer can affect the internal energy of the system. So we're going to talk about that, which is the first law of thermodynamics. Then we're going to apply that, right, to solve for the work done. Remember, same work done that we learned in um, physics 37 when we talked about work done as a mechanical means of transfer of energy. Here we're going to use that, so like let's say, in more complete um, concept of energy transfer due to a mechanical work or due to the change in temperature, and that can go into combine together into giving us internal energy of the system. Then we're going to talk about molar specific heats for gases. So specific heat, generally we use for the liquid and for the gas and for the solids, but then we can specifically use molar specific heat that is very unique to gases. Equipartition, equipartition of energy, which energy can be thought of as combination of translational, rotational, vibrational energies. So we're going to look at those degrees of freedom. And then types of processes that we can have in the system. So we're going to talk about adiabatic process. We're going to talk about isovolumetric, isobaric, isothermal, those different type of processes that we're going to be able to have in our system, and use the first law of thermodynamics to solve for the heat, work done, or different type of quantities. And at the very sort of like, let's say, the very last section of this chapter then talks about the heat transfer mechanisms. So it's like a specific three types of mechanism that we have, which is how do we transfer energy? So, or specifically heat. Well, we can do conduction, which is, so like a, physical touch, or convection, which is sort of like, let's say, motion of gases, or radiation. And this is generally can be considered as a energy due to the thermal energy, right? So like, let's say, when objects glow, right, they radiate energy, and that's a type of heat transfer that we will look at, as part of that three types of heat transfer mechanisms. All right, so let's then look at the first part of this chapter, which is in terms of heat, internal energy, latent heat, and um, basically type of energy that goes into doing two things. So it's going to do change in phase and change in temperature of a system. All right, so you can say, right, so we often speak of heat as though it were material that flows from one object to another. Well, it has been for a very long time, um, let's say, puzzled scientists in terms of trying to identify what is heat. And in 17th century, in 18th century, a lot of those scientists didn't really know what heat was. They could see that when you put two objects together, the temperature of the colder object increases, the hotter object decreases. But what exactly happening to cause that phenomena, they were kind of clueless about that. Um, One of the first theories to try to describe this was that it was some kind of invisible substance. They call it caloric, that goes from one object to another object because of difference in their temperature. So this is sort of like invisible substance that always goes from hot to cold, which makes sense because always the hottest one cools down, the cooler one warms up, right? So sort of like, let's say there's a direction of this motion of the substance. We can't see that substance, but that sort of like, let's say that object is changing changing temperature because of the either losing or gaining that substance. Obviously that was not entirely accurate. We do have change or exchange of something, but it's not some kind of invisible actual like let's say substance, but it's energy. So the energy is moving or transferring from one object to another, mainly from hot to cold. And the energy is the one that is responsible for changing the temperature, changing the phase of a substance. So that means, in terms of, let's say, what exactly happening between two objects of different temperature, energy transfer between them. So we kind of, touched on that in previous chapter when we talked about zeroth law of thermodynamics. We did say that if you put two objects together, um, let's say put them together right in physical contact or put them in the same system and they have a different temperature, there is going to be energy transfer between them until they eventually reach thermal equilibrium. All right, so remember I said that that's a zeroth law, and that's because our understanding of this thermodynamic processes have evolved after, let's say we came up with the first law and the second law. Then we figure out that there's another law that is much more fundamental than the first one and the second law. So we, instead of changing all the order, we call that a zeroth law, which pretty much tells you why the temperature is changing between two objects. They are in physical contact together but have different temperatures. So the energy is the one that is going from one system to another or one object to another. And that energy that specifically, right, that goes from one object to another object is what we call heat. Okay. So the unit of heat has also changed over time. Remember the caloric, that substance that I mentioned, right? So the original unit for this heat or that energy, right, that goes from one object to another was calories. So calorie is still used in in chemistry, right? In technically in physics too, depending on which class. So we still use this, but most of the time, what we do here is we use, you're gonna see, right? We're gonna use joules as a unit. But let's start with this. So original unit for the heat was calorie, and 1 calorie is the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. That means if you have 1 gram of water at, for example, 2 degrees Celsius, and you want to increase the temperature of that 1 gram of water by 1 degree Celsius, then you have to transfer 1 calorie of heat, right? The amount of the heat is 1 calorie into increasing the temperature by 1 degree Celsius. If you want the temperature to go down by 1 degree Celsius, we remove 1 calorie equivalent of energy. And that basically will then decrease the temperature. But that's kind of what we have. This calorie is just amount of energy moved from system or into the system or out of the system in order to change the temperature, for example. The calories, as I said, right, is still used in like some of the chemistry classes, for example, right? It's more, it's used quite a lot, but also it is used in food industry, right? So you buy anything in US, they are given in calories in terms of, like, let's say, amount of energy that they contain. So you buy, I don't know, a chocolate bar, and the chocolate bar has let's say 300 calories. So that means if you eat the chocolate bar, the chemicals, right, all the the basically the food itself can then give you 300 calories equivalent energy. How does that work? Well, you eat the food, the chemicals inside, or basically all this, the molecules, right, of the food, then all the chemical, and they contain chemical energy, which then converted by your body into a mechanical energy, and that mechanical energy allows you to, to, let's say, function. So that's why if you're, if you need to have energy, right, you have breakfast, you have good lunch, good dinner, and the food is basically sort of like the fuel for us, right? So we eat the food, and then we gain energy out of that, so we can go play, soccer, or tennis, or whatever it is, right? Because we get enough energy to do that. Try, not to eat anything for like a week or two. You're not gonna have any, energy, right, to do, any of those physical activities, because simply because your body doesn't have the fuel, doesn't have the energy that it needs to operate. Okay. All right. So one thing that we have about food, let's say, energy is this. So when you buy the chocolate bar, let's say it gives you 300 calories like that. But this is actually not the same calorie as I have over there, because this calorie, you can see, right? So uh, don't be fooled, right? That is actually kilocalorie. So this C, capital C, is technically is kilocalorie. So this 300 calorie is actually 300,000, let's say, actual calories. So what we have here is 300 calorie looks much better than 300,000 calorie. So when you buy it, when you let's say take the chocolate bar and look at the energy it has, and you see 300 calories, it doesn't seem that much. So you will be willing to buy it. But when you look at it and it says 300,000 calories, you will, probably be hesitant. Okay, that's a lot of calories, right? 300,000. So technically, this is nothing but some kind of, I don't know, like, let's say somebody came up with this idea, right, in one of those meetings. Let's make it calorie, but with a capital C, and that's, basically slashes the number by, 1,000, and what the customer see is pretty much 300. All right, so very good, let's say idea, right? Somebody came up with that, probably got a promotion because of that, but it allows the number to seem smaller, less scary, and it is indeed, right? So, but it is in terms of actual calories, it is still 300,000 calories. All right, so in terms of then what we have here is the calorie as a unit of heat was because of that caloric, the substance that I mentioned. And not until James Joule did an experiment to show that this substance, right, that we call caloric, that goes from one object to another to change the temperature, is actually nothing but energy. And what he did, he showed that the same thing you can achieve by doing a mechanical work. For example, here you have, let's say, a container with water. Okay, so the container with water has some kind of initial temperature. So you can put it on some kind of hot plate. So if I put it some kind of hot plate, then I can, kind of like old thinking, right? I can add that caloric into the water, which then will increase its temperature. Okay, that means in order to increase the temperature, we need some kind of caloric. That's that substance, right? That invisible substance. But Joule said no. It's it's basically energy. I can achieve same increase in temperature, the same amount of increase in temperature, if I do a mechanical work and just convert that to, let's say, heat energy. And what he did is basically he has, you can see, right? There's a pulley, there's a mass attached to the pulley on the other side that, we can, relative to the ground, calculate the potential energy, MGH. And then what we have here inside the water, we can see there's a paddle, right? And then as the object then, the potential energy, right? You know how much energy it has right now. You let go, it's going to fall down. As it's falling down, then you can compare how much energy you have for the object, and then that same amount of energy then basically convert it into water. So then as the basically the paddle rotates, right? As everything inside starts rotating, that the paddle interacts with water molecules. The collision creates friction. Friction creates some of the potential energy converted to heat energy. The temperature of water increases. And exactly same increase in temperature can be achieved because of that, the whole process, right? So because the friction now converts some of the collision energy into the heat energy, and the temperature of water increases. So he was able to show that mechanical work is equivalent to heat, let's say energy. That means energy coming from a mechanical, let's say, way, mechanical means, right, is exactly same as, from a different source in terms of, like, let's say, put it in a hot plate or something like that. So that's why what we have here is we have mechanical equivalent of heat. So, and he showed that falling object is, let's say, able to add energy into the system, same way as the hot plate can, and the temperature of the water will increase exactly same way. That means all it needs is, added energy. Doesn't matter how you add energy, as long as you add energy, temperature will increase. You remove energy, temperature will decrease. There's nothing invisible, substance or anything like that needed. It's just, pure energy going into the system or coming out of the system. So this equation is kind of like what we call mechanical equivalent of heat. It shows that 1 calorie is equals to 4.186 joules of energy. That means, remember that 1 calorie is the amount of energy needed to increase the 1 gram of water by 1 degree Celsius. That means 4.186 joules is the amount of energy in SI unit, right, needed to increase 1 gram of water by 1 degree Celsius. All right, so this was actually, um, very, let's say, important experiment. That's why the unit of energy is after, James Joule, right, because he was able to show that heat is just nothing but energy. So this is probably one of the most important, let's say, experimental results in all of physics, because this energy, right, then we also use in chemistry, we use in, let's say, biology, right, because we understand now that heat is just energy, and from that all this, everything else basically can be explained from that, right? So that means friction converting energy, let's say motion energy into heat energy, by, let's say, if you take your hands, right, you rub your hands like this, well, you can see, right, your hands get hot. Why? Because of the friction converts some of the motion energy of your hand into heat energy. All of these things can then basically explain why your, temperature of your palms increase. Well, because of the, energy converted from a motion energy into heat energy. All right, so now let's officially define heat. Heat is energy transferred from one object to another because of a difference in temperature. That means what one way we're going to talk about heat is when we say that the object temperature increased or decreased, then we can always assume that there was heat added or removed, because heat is just the amount of energy that was transferred into the system. Okay, so it's sort of like amount of energy that goes into changing the temperature. Later, we're going to see that you can also calculate heat that goes into, like, changing the phase. But the idea is that this is amount of energy added or removed from your system. Okay, so that's what we have. That's why it's amount of energy transferred, right? And the temperature, if you remember, right, of a gas is a measure of kinetic energy of its molecules. If you remember, right, this average translational kinetic energy was 3/2 times kT. This is a Boltzmann constant, K. So the temperature is nothing but average kinetic energy of your system. That means you have a system like this, you put a thermometer, and what it measures is basically average kinetic energy of your molecules. So if you add heat, which is, give your system some energy, then those molecules are going to be moving faster. As they move faster, average translational kinetic energy increases. That increase then will give you increase in temperature as well. So as the, average translational kinetic energy increases because your molecules inside gaining energy so they can move faster, well, that gives you increase in temperature as well. That's why if you remove energy from them, well, they're going to start moving slower, which means they will then have a lower average translational kinetic energy, and your temperature of your system will decrease. That's why you can think of, like, let's say, um, temperature is, as we said, right? So it's not just hotness or coldness, but in terms of average translational kinetic energy. And remember, we also have the internal energy, which was thermal energy, right? That was the total kinetic energy. So those are different things, right? Average kinetic energy and total kinetic energy, those are two different things. All right, so if you add all of those kinetic energies together, the sum, right? Sum total of all the energy of all the molecules in a substance is, then it's called its internal or thermal energy. That means, in a way, think like this. So not to confuse. So this is the average translational kinetic energy. How do we calculate average? Is we calculate kinetic energy of first one plus second one plus third one plus that plus, let's say ith particle. So you have I number of particles. So add all of their kinetic energies, then divide by number of molecules you have. Okay. So that means this is, or if you want, I can put this is like, let's say n, which is the nth number of particle, right? So this is what the average translational kinetic energy is. The total kinetic energy is what we have right here in the numerator. That's the total kinetic energy, because that's the total kinetic energy divided by number of particles. Then you get average translational kinetic energy. So make sure then it's clear. So temperature is a measure of molecules' average kinetic energy. Internal energy is total energy of all the molecules. And heat is the transfer of energy due to difference in temperature. Okay. So remember, so one of the things we have here is when we say total energy of all the molecules, well, a lot of times, remember, the ideal gas, especially like when we talk about, right? So we kind of, unless we considering real gases, right? We ignore all the other type of energies, like, potential energy or any type of energies, due to their elasticity or something like that. So generally, when we talk about energy, we talk about, let's say, kinetic energy. Okay. So when you're transferring energy, you can transfer different ways. We're going to see there are, two different ways you can transfer energy, and there are like three different mechanisms for that, right? But in terms of then what we have here is that it's important to understand the difference between temperature, internal energy, and heat. Okay, because a lot of times there's a confusion and students are confused, and there's like, let's say, not very good understanding between internal energy and heat. So make sure you guys are understanding this in terms of like difference, and let's say going forward, hopefully there is no confusion about that. All right, so here's then what we have. Internal energy of an ideal atomic gas. Remember, that's this idea, right? So ideal means that we are looking at in terms of their kinetic energies, right? So E internal is that's the kinetic energy, and then you have N, and that's a number of particles you have. So that means N times kinetic energy, N number of kinetic energies. Okay, and what we have here is this is nothing but the average translational kinetic energy. That means internal energy is N times average translational kinetic energy. But we also know that average translational kinetic energy equals, 3/2 kBT, right? Three halves kBT. That means if I replace this with 3/2 kBT, then internal energy is equals to then N times 3/2 kBT, or 3/2 N kBT. So again, I like to put B over here because K can also be used for other things. Hopefully there's no, so that there's no confusion, like in terms of what K, which K is that. So that's a Stefan Boltzmann constant, N is the number of, molecules or particles that you have, and T in temperature, which must be always in Kelvin. Okay, because that's not a delta T, that's just a T. Okay, we can look at in terms of change in internal energy, which then will be 3/2 NKB delta T. In that case, you can leave the delta T in Celsius because you are looking change in temperature, which gives you sort of like, let's say, change in internal energy. But when you're calculating internal energy at some state, for some specific state, this is just basically the temperature in Kelvin for that state. But this is an important equation. This equation tells you that internal energy of your system depends on only one of those variables that we have for the macroscopic system. Remember, the state variables are pressure, volume, and so like, let's say, temperature. So technically it depends on number of molecules as well, but number of molecules is the probably one variable that we change least. Excuse me. And what we have here is the temperature is, in a way you can say, right, is directly proportional to internal energy. So every time we have a change in internal energy, then we can say that it right away will tell us that there's a change in temperature. You cannot have one without the other. If you're changing the temperature, you're changing internal energy. If your internal energy is changed, that means the temperature is different, going from state 1 to state 2, for example. So that's kind of an important thing to remember, because one of the things we're going to see is when we get to the second law, the first law of thermodynamics, we are basically looking at the, internal energy with, relative to some other quantities, which we will see. But here it says that internal energy is proportional to the temperature of your system. And the only way you can change your internal energy in your system is if the temperature is changing. All right. So if the gas is molecular rather than atomic, um, that means basically it's not just a single atom, but maybe like a molecule, right? So then, besides the translational motion of your molecule, let's say atom, right? So, if you have just an atom like this, right? So it is just basically moving. You can have like, XYZ motion. Okay. But if it's a molecule like this, right? If it's a molecule, so like, let's say it's molecules usually have sort of like, spring type of or string type of, connection between them. Um, so then they can also, you can see, right, they can also rotate. There's also a rotational motion. Okay. And they can also, because it's sort of like a spring-like, elastic, force between them, it can rotate or it can just go back and forth, which means it can also vibrate. Okay. So that means not only translational, but also rotational plus vibrational kinetic energy. So that's your total, let's say, average energy, right? If you want to talk about it like that. So the average kinetic energy is in terms of average translational kinetic energy plus average rotational kinetic energy plus average vibrational kinetic energy. That means more complicated your, system is, right? Is it monatomic? Is it diatomic, triatomic, right? So every one, let's say, as you go and add more complexity, then you have to keep track of more, let's say, quantities, right? So we call them, we can see, right, we call them degrees of freedom in this case, right? You can see, right? So if you know that you're dealing with a molecule, then you have to understand that there's also rotational and vibrational kinetic energy that needed to be taken into account. Okay. Now, so here what we're going to do is this. Let's say we have a container with some water in it. So what I have here is I measure the temperature of the water that I have, where the MW represents mass of water. So if I measure the initial temperature, and then basically I have T initial, that's my initial temperature. Then if I want this, system or my water, right, to increase temperature or decrease temperature, so basically I have some kind of change in temperature, what I need to do here is, as we learned, right, to add heat or remove heat. Basically, we need to transfer energy in the system or out of the system in order to have a change in temperature. That means what I have here is this. The amount of water that I have in terms of its mass is becoming an important factor. The initial temperature and then the final temperature, basically by how much I want to change the temperature, that, the difference, right, we're going to see is becoming an important factor. So what we have here is this then. Q is the symbol for heat. It represents amount of energy transferred into the system or out of the system. And we can see from here is that heat Q is proportional to the mass of the substance. That means, for example, in this case, proportional to the mass of the water. More water I have, more energy I will need. Less water I have, less energy I will need. It's also directly proportional to change in temperature. Means that is the change in temperature am I changing by 10 degree or 100 degrees? Or let's say 20 degrees, right? So what is the change in temperature? By how much am I changing? If I change more, let's say that means, I go from, let's say 2 degrees to 20 degrees compared to 2 degrees to 5 degrees, then I need to add more energy. So that's why it's directly proportional to that. Then if we go from proportionality sign to equal sign, we're going to introduce a constant, and that constant is C, which we call specific heat. Okay, so that's a, sort of like that's a complete equation for the amount of energy needed to change the temperature of a substance while the substance does not undergo any phase change. By phase change, I mean going from liquid to solid, or solid to liquid, gas to liquid, and or solid to gas, right? Doesn't matter. As long as there is no change in phase, you can use this equation to calculate the amount of energy needed to change the temperature of a substance. Specific heat is a substance specific quantity. So you can see from this table, you have a specific heat in terms of kilocalorie per kilogram degree Celsius or joules per kilogram degree Celsius. I would say that this column is one that we're going to be using quite a lot. Okay. So for example, here's water. Okay. So for water, we know that for us, water is unique because um, when it changes phase, going from solid to liquid, liquid to gas, it happens in in a temperature that is, easy for us to see, for us to, let's say, uh, conduct an experiment with, right? So we can see that ice, or water, are going to be used quite a lot. So, for example, water at -5 degrees Celsius, for let's say it's in its solid form. So we have ice. Specific heat is 2100. So what it tells you is this. So specific heat is basically amount of energy needed to change the temperature of your substance. Okay. So let's say amount of energy needed, you can see, right? So let's say specific heat is equals to mass of water. Sorry. Let's say you can do like Q divided by mass of water times the change in temperature. That's how we can calculate the specific heat for, let's say, water. I take water. I know, let's say, how much energy I'm adding. So let's say 100 joules, for example. I'm adding 100 joules of energy. And I can find the mass of my water, right? How much I have. And then how much this 100 joules gives me change in temperature. Okay, so what type of change in temperature I achieved with 100 joules of energy added to the system, then that ratio will give me the specific heat of water. Now, if the water here is in a solid form, that ratio will give me 2100 joules per kilogram degree Celsius. If it's in a liquid form, that ratio is going to give me 4186 joules per kilogram. So you can see, right? So that's a liquid form. If we're dealing with steam, right? Water, let's say water in gas state, then that ratio will give me then 2010. Okay, that means each so let's say temperature specific phase will give me different type of specific heat for water. That means this is for a solid state, this is for the liquid, and this is for the gas. Okay, and as long as the substance is basically in the same phase, I can use this equation to calculate change in temperature. Okay. Now, one thing you probably will notice from this table is that generally water, you can see, right, seems to having like the highest specific heat from anything else in this table, and that's a really good thing for us because water was like I think 60%, 70%, right? That covers the surface of Earth. So the water has large specific heat, meaning it opposes change in temperature, and it requires a lot of energy to change the temperature of water by let's say a few degrees. The good thing about that is that This allows the temperature of water to only change slightly during the day and night. So for example, in California, right? So during the day, sometimes we can have 100, 110. During the night, same night, right? The temperature can decrease all the way to maybe 50 degrees. I'm talking about Fahrenheit. So 50 degrees Fahrenheit. That means we can go from 110 during the day to 50 during the night, which means then there's a really big shift in temperature. So heat will be removed, heat will be added during the day, heat will be removed, right, during the night. And amount of energy that transferred into the water and removes from water, if the water has a small, low specific heat, then that energy added or removed can be enough to, let's say, boil the water during the afternoons and freeze the water during the night. If, let's say, the water had that specific heat, for example, then we're gonna have a real difficult time, right? Imagine like during the day, the water is boiling in oceans, and during the night, it's basically, it's frozen. So it will be really, difficult, basically, to survive on Earth, right? Under those conditions. So that's why water having a large specific heat is very good for us, because the water, temperature of water in, let's say, oceans just maybe increase by 2, 3 degrees during the day and decrease by 2, 3 degrees during the night, but not by much. There's no dramatic change in water temperature because of the day and night, shift in the, let's say, in the temperatures outside. All right. So in terms of then what we have is this: you have a system, let's say that container with water, right? It's a closed system. If you have control over how much mass enters and leaves, right? So you can say that no mass enters or leaves. That means, amount of water that you have, even if it changes phase, goes into solid or gas or thing like that, let's say it doesn't change. Okay. So you have control, let's say, over the amount of substance that you have. Open system, then mass may transfer as well. That means, one of the things we have, if it's open system, then you can add things to your system, remove things from your system, in a way, not just energy, but the mass itself, right? So you can pour more water, remove some of the water can evaporate and escape into, let's say, into room, let's say environment and things like that. So that's why we have this. We have a closed system, open system, and isolated system, which is a closed system in which no energy in any form is transferred. That means in a closed system, mass is constant, but energy can be exchanged. Open system, mass can transfer as well as energy can transfer. Isolated systems is the one that no mass and no energy can be transferred in or out of the system. Okay. And when you have an isolated system like this, where you can control your mass, let's say, and energy transfer rates, right, and isolate them from environment, and let's say make sure that nothing leaves your system, nothing is added to your system, then one thing you can say here is the energy out of one part equals energy into another part, but all within the system. That means if your system is water and ice, let's say liquid water and ice, for example, right? So if here's your system, so you have liquid water, but then you also have let's say an ice cube. Then one thing we can say is that because this is within my isolated system, and isolated will be in terms of making sure that maybe there's like extra coating here that prevents any type of heat loss or transfer of mass, then any type of exchange between water and let's say liquid water and a solid ice will stay inside the system. Water will lose energy, so there will be heat loss because water is warmer and in contact with the colder ice cube, so it will lose energy. Ice cube is colder in contact with the warmer water, it will then gain energy. But where is that energy coming from? Well, it's same energy that coming from water. That means water transfers energy into ice cube, like liquid water. So it goes, and some of that energy, right, because they're in physical contact with one another, energy flows from hot object to cold object, or maybe hot portion or hot part of your system to a colder part of your system. But there's always going to be energy transfer, energy exchange, until your system is in thermal equilibrium. Okay, that's why you put an ice cube in water. Ice cube eventually melts, right? Because it's gaining energy, and it's gaining energy, it starts, increasing its temperature and then eventually changing phase and becoming liquid. But at the same time, your liquid, right? Your let's say iced tea or something like that that you have, well, it cools down. It's just now it's ice cold, right? It's nice and cold. And if it's summer, right, that's how we like to enjoy, right? So you have a cup over here with some liquid. You put some ice to make it cooler. Why? Because not because, let's say, water receives coldness from ice. No, it just water loses energy to ice, and when you lose energy, the temperature decreases. All right. So this is sort of like a system where we can prevent any type of mass escape or energy escape. That means this is an isolated system. Okay. So this is known as calorimetry. So the calorimetry is the type of system, technically, that you have let's say, some kind of beaker or a container, right? That has water in it, and you have a thermometer that can measure the temperature of water, but also you have a calorimeter cup. So this cup generally is, aluminum or copper, depending on, the type you have. So what you have here is, you can assume that the cup and water are in thermal equilibrium with respect to one another. Okay. That means what you have here is, so let's say in this case, because the cup and the water in thermal equilibrium, even if they weren't in thermal equilibrium, eventually they will reach thermal equilibrium. One of the things we can have here is, we can say that if you initially start with water a little bit cooler than, let's say, the cup itself, then you can say that energy exchange, net energy, is going to be zero in your system, which means that heat gained will be equal to the heat lost. Okay. So which one will lose heat? Water, because it was, warmer. Which one will gain heat? Then, the cup, because it was a little bit cooler. The idea here is, eventually, right, your system will reach equilibrium. So you put the water inside the, this calorimetry, right? And, you wait 5, 10, 15 minutes, then you can say that eventually those two things will reach thermal equilibrium. Okay. That means most of the time when we're considering calorimetry, we always can consider that the water and the cup together is in thermal equilibrium. Okay. Then generally this system is used to find, for example, specificity of some kind of unknown metal. I can take an unknown metal here, maybe like a cylindrical metal, and put it on some kind of hot plate, increase its temperature to some, I don't know, let's say 200 degrees Celsius or something like that, and then take it and put it inside. Okay. And I have then this cylinder, unknown cylinder here. Then what I have here is this. I have three things in my system: the cup, water, and this metal. So then I can say that energy of the cup plus energy of water plus energy of this metal will be equals to zero. That means sum of their energies. So Q cup plus Q water plus Q metal equals zero. Well, obviously you cannot get zero if you're just adding all together, all of those, and they're all, positive. Remember, heat is energy. Energy is a scalar. So there is no like direction or anything like that. So, but they can be positive, negative. When is it positive? It means energy is gained. When it's negative, it means energy was lost. Obviously, we can see, right? If you have a water and a cup roughly around 23 degrees Celsius, and a metal that roughly about 200 degrees Celsius, well, metal will be the one that will lose energy because it's in contact with a cooler, let's say two other cooler objects. Water and, the cup then will gain energy because they are in contact with a hotter object. That means this guy will be negative, the other two will be positive, and sorry, this guy will be negative, Q metal, and other two will be positive. So then your equation then will be complete. Okay. That means energy will be gained here, G for gained, and energy here will be lost by the metal. Okay. But amount of energy lost by the metal cylinder is exactly equal to the amount of energy gained by the water and the cup combined. Okay, so then we can use this to calculate specific heat of this unknown metal and things like that. So we're going to see an example of that. All right. So this is a very useful diagram, because one of the things we have here is when you add energy into the system. So let's say, I'm going to give you in terms of this. So let's say we have an ice cube. Okay, let's go back. So let's say we have an ice cube here. Okay, and this is ice cube, which is initially at negative, let's say negative 40 degrees Celsius. Okay, so we're going to start with negative 40 degrees Celsius. Well, what I have here is this. If I want to increase the temperature of this ice cube from negative 40 degrees Celsius all the way to, let's say, I don't know, 150 degrees Celsius. Okay. Can I use this equation where Q is equals to mass of ice cube times specific of ice cube, then times delta T? So I don't know, let's say it's 50-gram ice cube, right? So that means, let's say, for example, this will be 0.050 kilograms, converting kilograms, right? Specific heat of ice was 2100 joules per kilogram degrees Celsius. And change in temperature, then let's say I put like 150 minus 40. Okay, now the question is that can I use this equation to calculate that, going from negative 40 to 150? Well, the answer is no. We cannot do this. And the reason we cannot do this is because between negative 40 and 150 degrees Celsius, there are other things happening that is, not a change in temperature. That means there are other, let's say, things happening when you add energy, mainly changing phase. Because we know that between negative 40 and 150, there is 0 degrees Celsius and there is 100 degrees Celsius. What are those two, temperatures, let's say, famous for? Well, this is melting point of water, and this is boiling point of water. That means what we have here is when you go from negative 40 to 0, at 0 you have to undergo changing phase from solid to liquid. Then when we go and reach 100, you cannot go 150 without undergoing another changing phase. In this case, liquid to a gas. So that is why that one equation where Q equals mc delta T going from negative 40 to 150 will not work, because that does not include, changing phase. All right. So changing phase requires much more, so like, let's say, steps than that just one equation. And I'm going to use this diagram to pretty much demonstrate that. So again, let's go back over here. Let's say that, we can't use that. So let's forget about that. Make sure that you know that we can't use that. So what we're going to do here is this. We're going to start with negative 40 degrees Celsius ice. So that's going to be our starting point. Okay. Then what I can do here is this. I'm going to able to add energy into the system. So let's say you have here's a system, right? You have ice. Okay. I'm going to add energy into this. Okay. Maybe put it on a hot plate or something like that. I put it on a hot plate. So then I'm adding heat. Okay. So, and when I'm adding heat, right? I don't like this. Okay. When I'm adding heat, then temperature increases. Well, temperature increase will take ice from negative 40, so you can see, right, from negative 40 to all the way 0 degrees Celsius. And it cannot go beyond that, because every time ice reaches 0 degrees Celsius, it cannot increase the temperature beyond that, because there is no such thing as ice at 1 degree Celsius or 2 degrees Celsius. Ice has a limit for the temperature, and that's 0 degrees Celsius. In order for you to have that, that ice as a, sort of, it's still water, right? So in a solid form. For it to go to 1 degree Celsius, it has to melt first. So that's why what I have is this. This is going to be segment 1. For segment 1, this is going to be Q1. So this will be the amount of energy that will take ice cube at negative 40 degrees Celsius all the way to 0 degrees. So this will be mass of ice, specific of ice, times 0 minus 40. So this will be energy required for that stage 1, taking the ice from negative 40 to 0. That means right here I have ice at 0 degrees Celsius. What do we do next? Well, next we need to then deal with what we call latent heat. So the latent heat is then amount of energy that goes into changing the phase of a substance. Okay. So when you change the phase of a substance, then what we get here is that equation is proportional. So this is the equation for the latent heat. Let me put it like this. It's proportional to then the mass of the substance. Okay. It requires, so like, let's say, how much to know how much substance you have. And the proportionality sign to equal sign, which is a constant. And that constant is what we call L. L is the latent heat. Okay. So the L comes in 2 types. There's a heat of fusion and heat of vaporization. We're going to talk about that, but let's say in this case, what I have here is for stage 2, which is, for this stage, I need to have what we call heat of fusion. Okay, so this is heat of fusion. Heat of fusion represents amount of energy that goes into melting or freezing a substance. Okay, and it comes with plus minus, because energy that comes from this equation doesn't have, let's say, built-in plus minus. See, for example, for this energy, Q is equals to mc delta T. Delta T kind of has a built-in plus minus inside. If temperature increases, delta T is positive, Q is positive. If delta T decreases, Q is negative. So delta T is negative, so Q is negative. But in terms of then M times LF, it doesn't have that. So you have to manually put positive or negative, depending if you're melting or if you're freezing. Right now, because we're melting, so we can put positive like that. That means this is for my stage 2. I can put like here Q2, stage 2, where in order for me to continue, right, my journey from negative 40 to 150, I need to melt the ice. And stage 2, this equation gives me, mass of ice times heat of fusion. That will give me the amount of energy needed to melt the ice. Okay. Now, what I get here is, this was stage 2. Now I'm right here. This represents, now I have water at 0 degrees Celsius. That means now I have water at 0 degrees Celsius. Well, water at 0 degrees Celsius, in order for it to go and increase temperature, we need to add heat. And again, this equation is the equation that needed to increase the temperature of a substance, without changing the phase. That means this is stage 3, where I am, it's all liquid, right? You can say it's all liquid. Then I'm taking the temperature of, liquid now from 0 to 100 degrees Celsius, whereas this is going to be now water at 100 degrees Celsius. That means going from 0 degrees Celsius to 100 degrees Celsius, that's stage 3. And this is equals to the mass of ice times specific of water, then times 100 degrees minus 0 degrees. And that will give me the amount of energy needed to increase, let's say, this guy, then now that it's water, it still has the same mass. But, now we have to use a different specific because it's in its liquid form. And this equation takes the water from 0 to 100 degrees Celsius. And gives you the amount of energy needed to do that. Then what we do, we get here, where we have water at 100 degrees Celsius. In order to then go from 100 to 150, we need to first evaporate all that liquid water we have. So then you can say, right, then this region here represents that, water and steam. That means this is the, the point where water, liquid water and the steam, right, they're in equilibrium. That means while you're evaporating the water, your substance has some water, some steam. That means it's some of that, it's in liquid form, some of that steam form, right? And eventually all the liquid is becoming evaporated. Okay, that means you basically slowly go, and as you get closer and closer, more of the substance then in gas form rather than, let's say, liquid form. Let's call this stage 4. So energy for stage 4 will be again equation for the latent heat. So mass of water times heat of, in this case, vaporization. So this is heat of vaporization, which means that we are looking at, converting from liquid to water. So liquid to a gas, liquid to a steam. Heat of vaporization. There you go. And again, we put positive because we are adding energy to vaporize it. Okay. Then we get to this point now. We're finally here, and this is basically water at, we are gas at 100 degrees Celsius. That means all the water, all the liquid water now evaporated and it's in gas form. Okay. So then stage 5 will be to take that gas and increase its temperature to desired 150 degrees. That means this will be then Q5, which is the stage, for the stage 5. So mass of steam, right? Now mass of steam times specific heat of steam, then times 150 minus 100. Then this will give you then amount of energy needed to achieve that. It means get to this point over here, which is 150 degrees, which is our final desired temperature. As you can see, right, in order to get that, we needed energy for stage 1, energy for stage 2. That means we needed to increase temperature of ice from -40 to 0. Then we need to melt the ice. That's stage 2. Then take the melted ice, which is now water, liquid form, and increase its temperature all the way to 100 degrees. That's stage 3. Then you need to evaporate that liquid water, stage 4, which then evaporate all the liquid water now to steam. And then finally, we take the energy and add to system to take the steam from 100 to 150. And summing all that will give you the net amount of energy. So that's why you can just use one equation to calculate from -40 to 150. It's a 5-stage process because there's a melting and there's a boiling between those two temperatures. So we have to take all of those into account because we have two types of equations. Q1, Q3, and Q5 are the equations where there's a change in temperature. And we use this equation, Q is equals to MC delta T. That's the change in temperature equation. But for the Q2 and Q4, then there is a change in phase. And for that, we use this equation, Q equals plus minus times L. And L can be LF or LV, either, vaporization or fusion. That means make sure you understand you're dealing with two different types of heat equations. One to change just the temperature of a substance without undergoing any change phase. The other one only undergoing change phase without changing the temperature. All right. So the table with all the latent heat values and heat of fusions and things like that. So, and also the melting point. So again, so we had the water, 0 degree is the melting point. In terms of then kilocalorie per kilogram is 79.7 for heat of fusion. But what we want is this, 333 kilojoules per kilogram. That means 333,000 joules per kilogram. Then what we have here is that means this is going from a liquid, from solid to liquid. And then here at 100 degrees Celsius, this is then needed to go from a liquid to gas. One thing you will see that this number is almost 10 times more. That means there's almost 10 times more energy needed to evaporate, the substance than, let's say, melt. So this is 2,260, but kilojoules, which makes it, roughly 2.3 megajoules, million joules. Okay. And you can see, right, then what you have is that the other substances, for example, oxygen melts at negative 218. Nitrogen melts at negative 210 degrees Celsius. For example, then iron, it's a solid form all the way to 1808 degrees Celsius, right? So tungsten, 3,410 degrees Celsius, right? So that means you can see in terms of what we have is water is one thing that, it's kind of like simple for us to uh, absorb in a room environment, because even the 100 degrees Celsius, so we cannot really survive 100 degrees Celsius, but we can have a container where the water is inside is in 100 degrees Celsius, and we can absorb it, evaporating. All right, so here's an equation for the latent heat. So Q is equals to M times L. And again, there is a plus minus, indicating, so plus basically means this is melting or, evaporating. And minus means then freezing and condensing. Okay. That means if you know that you're going from or you can say that plus is solid to a liquid and liquid to gas, where minus here is liquid to a solid or a gas to a liquid. So then you can have that. All right. So problems solving calorimetry. Remember, this was the problem that involved isolated system with mass and amount of energy unchanged inside your system. That means the total energy of your system is conserved. It's just converted from, or actually not converted, but transferred from one part of your system to another, or one object from your system to another, but everything is within your system. So that means you want to know, is it isolated or not? Can I apply this technique? Okay. So are all significant sources of energy known or calculable? If the answer is yes, apply conservation of energy. If no phase change occur, the heat transfer will depend on mass, specificity, and temperature of change. That means Q is equals to MC delta T only. That's it. If there is a phase change, then Q is equals to M times L. If there's both temperature change and phase change, then you combine both of them. So you can see, right, in terms of then what you have is, you can think of, like, let's say there's the system, isolated system, then identify the type of substances you have in your system, because you can have several things are mixing. You can have, water and ice mixing. You can have water and aluminum mixing. You can have a, calorimetry cup with water, and then you mix something else with that. So all of those things you have to take into account. Okay, make sure that every term is accounted for, every type of energy accounted for. Is it changing temperature, changing phase, and all of those things. Okay, so and a lot of times, that if you leave all the objects within your system in contact for a very long time, there's going to be one final temperature, for all of them. That means they will all eventually reach thermal equilibrium. So then we can use that to solve either that temperature or, other things that are unknown for the problem. So latent heat of vaporization is relevant for evaporation as well as boiling, right? Because that's basically happening at 100 degrees Celsius. Okay. Or you think like this, it's 100 degrees Celsius for water. I want to make sure that it's clear. It's for water. If you have, I don't know, let's say ethyl alcohol, then it's different temperatures, right? So for them, it's not 100 degrees relevant, right? For ethyl alcohol, the boiling point is 78 degrees Celsius. Okay, 78 degrees Celsius, it, evaporates. Um, so that means you have to kind of like understand what type of substance that you're dealing with. The heat of vaporization of water rises slightly as the temperature decreases. On a molecular level, the heat added during change of phase, change of state or change of phase, same thing, does not go to increasing the kinetic energy of individual molecules. That's why the temperature doesn't change, but rather to breaking the close bonds between them so that the next phase can occur. Okay, so you can kind of think of it like this. So for the uh, ice cube, right? So you have so like a solid and ice cube. Those are the molecules, and they are all bound to one another with sort of like, let's say, spring-like, forces. So they can keep the shape, and that they can keep the volume. That means they can vibrate a little bit back and forth, let's say relative to one another, but that springs keep them all together. Okay, that means basically just a little bit, maybe back and forth like this, but other than that, it maintains its shape. But here's the thing: if I add enough energy to the system, then this vibration, so let's say this molecule that is here can go over there, this one here that can go over there, and they can then stretch the spring, right, that keeps them from the other molecules to extreme, and you can deform it, you can basically break it, right? So that's basically breaking uh, those bonds between them. So if you give them energy, that's why, for example, ice, if you give energy, it can all the way to 0 degrees Celsius, it can still keep the shape. But beyond 0 degrees Celsius, when we add more heat, every energy goes into them breaking those bonds between them. Then when the bond is broken, then you can think of, like, let's say, instead of spring, you have them in terms of liquid, they are bound to one another by, instead of a spring, you can think of, like, let's say, they're bound to one another by strings. Let's say they're bound to one another by strings, and the strings are, unlike springs, they're not restoring. So I mean, they're just bound to one another, but they can go over one another, they can take the shape of the container and things like that. Okay, so they cannot maintain the form anymore. Okay, they cannot maintain the volume, so they have to take the volume of the container. And if I add more energy, even more energy, right, then they will start moving even faster relative to one another, and they can break away from those strings as well. So in a gas form, you can think, like, let's say those molecules are completely free from one another, and they're moving far apart from one another, random direction and things like that. That's because all that energy, right, added allows them to break those bonds, right? So faster they're moving, easier for them to break bond. And then when I remove energy, slower they're moving. Then when they collide, they can actually stick together and things like that, and generate those molecular bonds between them. All right, so that's kind of like, let's say, what happens at the molecular level. Let's look at an example. You have a Carlos that takes a 10-kilogram bag of ice at negative 10 degrees Celsius from the freezer and puts it in the back of his truck. Unfortunately, he forgets about it and the ice melts. How much heat energy did it take to melt ice completely? Okay, so what we have is this. So Carlos, we don't care about Carlos, but let's say what we have here is what we're interested in is the bag of ice. So we have 10 kilogram of ice at initial temperature of 10 degrees Celsius. That means we're given mass of ice, which is 10 kilograms, and initial temperature of negative 10 degrees Celsius. Then it says he forgets about it, right? Carlos forgets about the ice, and ice melts. Okay, that means if ice melts, that means we can think of, like, let's say that indicates that the final temperature, remember, the ice can only melt at 0 degrees Celsius. And we're not given anything else. We don't know if the once it melts become water and then the temperature of water increases. No, we assume that that's where we stop. It melts the ice. That means our final temperature is 0 degrees Celsius. Going to that diagram, we want to see like, okay, so this is temperature, this is heat, let's say. How many segments we have? Well, let's say we started at negative 10 degrees. So this is where we start, right? Negative 10. Remember, this is 0. And somewhere over here is 100, right? So we start negative 10. So first, in order, before it can melt, it should go and increase temperature all the way to 0 degrees. That means there is, stage 1. An equation for stage 1 is just a change in temperature. So it's mass of ice, specific heat of ice times delta T. From delta T from, 0 to negative 10 to 100. So 0 minus 10. Then it's going to have to melt the ice. So then there's a second stage. Melting is changing phase. So then there's a stage 2. But we kind of stop here. We don't go beyond that. That means our Q2 is equals to mass of ice times heat of fusion. And we stop there because we know we're just looking at up to that point. How much heat energy did it take to melt the ice? Will be sum of Q1 and Q2. That means Q net just takes into account changing the temperature of ice from negative 10 to 0, then melting the ice. So this will be Q1 plus Q2, mass of ice, specific of ice, times, let's say that times delta T, plus mass of ice times heat of fusion. So this will be 10 kilograms times then specific heat of ice, which is 2100 or 2090, they're pretty much the same, joules per kilogram degree Celsius or degree Kelvin, same thing goes well because it's a delta T. So then you have 10 degrees Celsius because it's from 0 minus 10 gives you 10. Then plus mass of ice, which is again 10 kilograms, then times heat of fusion. And this is 333, remember, times 10 to the 3 joules per kilogram, or 3.33 times 10 to the 5. Either way, you can write it, right? As long as it's, 333,000. Okay. We calculate this, we're going to get 3.5 times 10 to the 6 joules, or 3.5 megajoules. That means 3.5 million joules needed to, melt this ice. And that's a lot of energy. Well, that's because there are a lot of ice. 10 kilogram of ice is a lot of ice to melt. All right, so that's this problem over here. All right, so let's look at another one. Okay, so for this one, we have 0.05 kilogram ingot of metal is heated to 200 degrees Celsius, and then dropped into a calorimeter containing 0.4 kilogram of water, initially at 20 degrees Celsius. The final equilibrium temperature of the mixed system is 22.4 degrees Celsius. Find the specific heat of the metal. Okay. Now, one of the things we have here is this. So it's an isolated system where I have a calorimeter with some water in it, right? So let's say I have some water in it. Not green water, but let's say some blue water like that, right? And the temperature of water initially is 20 degrees Celsius. And then the temperature, so let's do this. So, okay. Temperature initial of water is 20 degrees Celsius. And then we have the, let's put the mass of water, 0.4 kilograms, so 400 grams. Then we have this, 50-gram ingot. So mass of the, I'm going to put M for metal, right? Mass of metal is 0.05 kilograms. Initial temperature of metal is 200 degrees Celsius. Okay. And once we mix them up, the final temperature is 22.4 degrees Celsius. And then the T final of the water is going to be same as T final of the metal. And there's going to be 22.4 degrees Celsius. Now, I mentioned that when you have a calorimeter, then you also have to take into account the cup itself. Okay. So, and the cup here is, in this case, basically is this guy over here, right? Because it's isolated from environment. The only thing here is that we don't know what type of cup it is. Is it aluminum? Is it copper? And things like that. So if that type of information is not given to you, then you can say that maybe amount of energy that has been absorbed by the cup is negligible compared to everything else. Okay. That means what you have here is, you can say that in your system, there's only two things: the cup, sorry, the water and the metal. The cup can be ignored in this case. And what I have here is that because, again, my system is isolated, I can use the conservation of energy. I can say that Q net equals 0, where it's Q um, water plus Q metal will be then equals to 0. Okay. Now, what I have here is Q water is water from 20 degrees Celsius to 22.4 degrees Celsius. I can clearly see there is no change in phase. That means I can say that that equation involves mass of water, specific of water, then times delta T at the, sort of like more or less room temperature. So no change in phase. Then plus mass of metal, specific of metal times delta T, and this is equals to 0. And my goal in this problem to solve for this, find the specific heat of the metal. Okay. That means that's the quantity that I want to find. Now, what I can do from here is then this. Isolate this, so M of metal, specific of metal times delta T is equals to negative of mass of water, specific of water times delta T. Then put like this is for the metal, this is for the water. Okay. And obviously you can say, right, just divide both sides by mass of the metal and change in temperature of the metal. If I do that, so this cancels out, and then allows me to calculate specific of the metal. So specific of the unknown metal will be then equals to negative mass of water, and that was zero point 0.4 kilograms, times specific of water, 4186 joules per kilogram degrees Celsius, change in temperature of water, which is 22.4 minus 20 degrees Celsius. Then in the denominator, I have mass of the metal, which is 0.05 kilograms, then times the change in temperature, which is 22.4 degrees Celsius minus the initial, which was 200 degrees Celsius. Now you can see, right, okay, so there's a negative over there. So how come? Well, that negative ends up canceling out with this negative over here, because I have a lower temperature minus higher temperature, I'm going to get a negative number. And negative, negative, going to cancel each other. So specific heat cannot be negative, it's just a positive quantity. But if I plug in everything here and calculate, then I will get the specific heat of 453 joules per kilogram degrees Celsius. Okay. And that's the specific heat of this, unknown metal. All right. And this is actual experiment. A lot of times we do this experiment in class. We do, however, include the cup as an object. So that becomes also, Q cup plus Q water plus Q metal equals 0. So it's, during the labs, we do a little more sophisticated lab where the cup cannot be ignored, because, we can see, we can basically either be given or we can tell what type of material it is. So, and we can use that information as small as the, let's say, contribution of that cup, taking that into account is probably a much better idea. All right, so here's one more example. A 65 cubic centimeter block of iron is removed from an 800 degrees Celsius furnace and immediately dropped into 200 milliliter of 20 degrees Celsius water. What fraction of water boils away? All right, so in this example, so we have, again, we can assume that this is isolated system. So you have one object that has initial temperature of 800 degrees Celsius, going to be dropped into another object, which is basically, a container with, there's a, 20 degrees Celsius water, 200 milliliter, right? And some of the temperature, some of the water then will boil away. Okay. Which kind of gives us, a hint that, uh, let's say when temperature needed for the water to boil away is 100 degrees Celsius, and not all the water is boiling away, because that's about fraction, that means the temperature doesn't go beyond 100 degrees Celsius. That means when we mix this, block of iron with water, we're going to get final temperature of 100 degrees Celsius, which then boil away some of the water, but not all of it. That means, remember, 100 degrees Celsius is the temperature where water can be in equilibrium with respect to its liquid and gas form. And you can have some of the, substance, like in this case, water, right? Some of the water can be in a liquid form. Some of them can be in a gas form. And what we're going to do here, we're going to then find how much of the mass is now evaporated. And then we can basically, since we know how much we have, so we can then find out, let's say, the percentage, right? What the fraction of the 200 milliliter now has become steam. Okay, that means what we have here is we have basically interaction between two objects, a block of iron and water. And again, same thing we can do is we can say Q for water plus Q for iron, right? In this case, Fe for iron, then this is equals to 0. Okay, that means their sum will give me 0. What I have here is then mass of water, then times specific heat of water times delta T. However, there's also some, evaporation going on. That means this can also be plus mass of water. So this is basically going to be the mass of water that becomes steam, right? So put like as C for steam. Then LV, which is heat of vaporization. So those two together is just Q water. Okay. Then plus, because we don't assume that iron is going to undergo any type of phase change. So it's going to be mass of iron, then times specific heat of iron, then times delta T equals 0. Okay. Now, what we have here is this. We know the mass of total mass of water. We know the initial temperature of water. We know then the final temperature of both of them is then 100 degrees Celsius, and we have also initial temperature of the iron. Okay. Now, we're not given how much iron we have, but we are given the volume of the iron block, 65 cubic centimeters. But since we know it's iron, we can find its mass by just using the density of iron is equals to mass of iron divided by its volume. So using this equation, then I can easily solve for the mass of the iron, because density, for the iron is a known quantity, and then we can easily solve for that for the mass. Okay, so let's solve for that. Mass of iron is equals to the density, which is 7,870 kilogram per cubic meters, times the volume, which is 65 cubic centimeters, which we can then convert, where 100 centimeters is 1 meter, and then we cube this as well. And then we can find the mass of the iron to be 0.512 kilograms. That's the mass of the iron. Okay, that means I pretty much have everything that I need. The only thing, maybe we also need to convert the 200 milliliters of mass of water from 200 milliliters into kilograms. Okay, where 200 milliliter is basically can be converted into, again, using the same equation, right? So I have mass of water is equals to density of water, because 200 milliliter is just volume, right? Then times then the volume of water. So it's 1,000 kilogram per cubic meters. And then we have 200 milliliter. Okay. Where I can have then let me write this actually in terms of times 10 to the negative 3 liters. Okay. Where then I need to then convert from liters to cubic meters, where I can say that 1 liter is 0.001 cubic meters. Okay. All right, so then the liter is going to cancel out. Then I'm going to get a cubic meters and then times 1,000. Then I can get mass of water converted into, SI unit of 0.2 kilograms. That means now that I have mass of water, I have mass of the iron, those quantities then can be used because here I have mass of water, specific of water times delta T plus mass of the steam times LV plus mass of the iron, specific of iron times delta T equals 0. And then just solve for this guy, remember. So I can say mass of the steam times LV is equals to, move the other two to the right. So minus mass of water, specific of water times delta T plus mass of the iron, specific of iron times delta T. Then this is divided by then LV. If I divide both sides by LV, then I can get mass of the steam. Okay. So from here, mass of the steam is equals to, so negative, then I can plug in the values, right? So here I can have 0.2 kilogram for mass of water, 4186 joules per kilogram degrees Celsius. Then change in temperature. So change in temperature will be 100 minus 20. That's because, my final is 100 degrees, right? So plus, so remember, so I'm basically using a bracket here. So plus, then 0.512 kilogram, then times specific of, iron, which is 449, then times change in temperature. Well, in final is 100, initial is 800. Okay. So that's where this negative going to cancel out. Coming from that. Delta T for the iron is going to be negative and it's going to cancel out. So then divide by LV. And LV here is, 22.6 times 10 to the 5 joules per kilogram. Okay. So then if I solve for mass of the steam, we're going to get 4.15 times 10 to the negative 2 kilograms. Okay. And that's basically 0.0415 kilogram, and my total was 2.200 kilograms. So basically I have about 40 grams of the water now converted to steam. And you can see, right, total I have about 200 gram. So you can kind of like, let's say then say, the fraction here is 4 or 0.0415 over 0.2 times 100%, we're going to get roughly 21%. That means 21% of the water now is in steam form, 79% it's in liquid form. All right.